Good afternoon, ladies and gentlemen. It's great to see such a big crowd. Lovely day here in Sheffield. I was a bit confused when I got to the tram stop because I thought I've never seen Sheffield in the sunshine before. And is it the right place? Yes, it was the right place. So the talk today is going to be about what's probably the most popular group of fossil invertebrates, the trilobites. Beautiful creatures, long extinct. And I'm going to be talking about exceptionally preserved examples of trilobites and what we can learn about them when they were alive. Why the talk? So the inspiration for this talk comes from a visit here a couple of weeks ago when I came to use the X-ray microscope that belongs to Neo-Jurassica. It's just along the road down there. And I brought a specimen to make a 3D scan of. And it's something I had scanned already in 2014, but I've lost access to that scan. So I thought we'll just do another one. And the picture on the right is an image of a trilobite. It's from the Ordovician of New York. And what I've done there is from the scan, extracted the complete three-dimensional pyritized trilobite. And you can see in yellow, it's got a complete antenna. And you can actually see it on the surface of the specimen at the top, just the proximal part of the antenna. But with a 3D scan, we can follow it all the way around and see it in 3 dimensions. And I've shown the eyes here in blue. So pretty exciting, very, very rare indeed, and a really good excuse to give a talk about trilobites. Right, this is the plan for the talk. 3 sections. So I'm going to start off introducing trilobites to you. What are they? Why are they so special? Why are they so popular? I'm then going to go on to a middle section where we'll talk about the exceptionally preserved specimens where you can see all of the usual, well, rarely preserved details, the soft-bodied parts that you almost never see in the fossils. And then the final section will be about bringing trilobites back to life. What did they do with all these soft parts, all these legs and antennae? And what traces did they leave of their activities during life? And I'll show you some reconstructions of trilobites. So that's the plan. And if we start with trilobites, what are they? Who here has actually ever found a trilobite fossil? That is quite a few people. Who'd like to find a trilobite fossil? Not everybody? Yeah. Everybody. They're really, really charming, and they can be found if you go out there. So trilobites. So I recently read in a book someone talking about geological time in terms of galactic years, which I had never heard of before, but I really like it. It's quite a fresh way of looking at it. So that is the time for our sun, our solar system, to go all the way around the galaxy. And it's about 225 million years. So trilobites, they were on Earth alive for a bit over one of those galactic years, between about 521 million years and 252 million years. And then they've been extinct for the galactic year since then, ever since 250 million years ago or so. They're arthropods, so something like a woodlouse that would be familiar from your gardens, made up of a body with lots of different segments. They've got a hard outside exoskeleton made of calcite. They, like arthropods do, as they grow bigger, they shed the old skin and then add a new one as they're bigger. So what you typically find when you go looking for them are the shed parts of that exoskeleton as the animal was growing. They've got incredible eyes. We're not going to be diving deep into anything during the talk, but I'll just give a few illustrations, essentially made of little calcite crystals. They lived in lots of different paleo environments. So they lived on the sediment surface, and some other kinds lived in higher in the water column, swimming. They lived in deep water. They lived in shallow water. So they lived in lots of different types of paleo environments. So here I've put 4 different images of examples of the same species. It's an Acastoides from the Devonian of Morocco. And can you see what's happening from left to right? It's illustrating one of the properties of trilobites, and not only trilobites. Think back to what you can find in your garden. Can you see what's happening there with that trilobite? So it's it's coiling up, isn't it? It's rolling itself up to this protective stance over here. And I've labeled on the different views some of the main bits of trilobites. There are many more names than this, but just as an introduction, you can see there's a cephalon over there, which is its head shield. And then there's a pygidium, which is the tail shield, if you like, at the other end. And there are all these thoracic segments in between. And here are the eyes. And you can see why they're called trilobites, because they've got these three lobes, haven't they, down the axis. They've got a central axis, and they've got these two pleural regions on each side. And what you might think of as its nose, not really a nose, but in that position, a glabella. And then what I've not labeled, there are three cheeks. So when it molted, that side cheek with the eye would fall off, basically. So you can find those separate pieces with beautifully preserved eyes. And that is a woodlouse. So it's not very closely related. It's another arthropod. It's a different group entirely. It's a crustacean. But it just shows how very similar that tactic is when there's danger. Close up. You can see the little eyes over there and the little tail tucked in. And one of those charming features of trilobites. All right. So eyes. I mentioned the eyes. Clarkson, Ewan Clarkson, he has written many papers on the eyes because they're truly fascinating. So the picture at the top left there, you can see it looks a bit like a Dalek. It's got all of those spherical lenses. Each one of those is a crystal of calcite. And if you look really close internally, it's got a beautiful internal structure with two different kinds of calcite to correct for the spherical aberration, to focus. So super, super advanced. And not all of them had those eyes. So some of them had no eyes at all. And this guy down here from Wales, called Trinucleus, was completely blind. So living in deeper water, pitted shield, quite a different looking kind of creature. And this picture over here shows different groups of trilobites down here, the orders of trilobites, time from the Cambrian at the bottom all the way up to the Permian over there. And that kind of eye that we see top left is shown here in red. So it's just one of the groups called a group called Phacopida. And then this stippled pattern is something more like a dense mosaic of little lenses. That's called holochrole. The other one's called schizochrole. And just to point out this one up in the Carboniferous, so that's a Yorkshire trilobite. That's something called Paladin eichwaldi shunnerensis, after Great Shunner fell up north, a place that I only know in rain and fog. But if you can tough that out, there are beautiful trilobites to be found. So I'm going to show you two more pictures of trilobite eyes. And this one I found fascinating. You can see in the side view, look at the eyes. You see they're like a tower. So this thing has got like tower eyes. And there's a paper by Forty and Chatterton that looked at that and worked out that actually it's got a little eye shade. So if you shine the light from above, like in that picture there, you see there's none of those lenses are now illuminated. So that's the eye of a trilobite that wants to look sideways. So it looks horizontally and doesn't want the distraction of light from above. So tower eyes with an eye shade, quite incredible, from the Devonian of Morocco. And these are the other kind of eyes, the holochrole eyes, the kind of densely packed mass of little lenses, like you might see on a dragonfly if you look up close at a dragonfly eye. But look at this one. You can see here the great big long fields with lenses. And when you can look at it sideways, that trilobite could see in almost all directions, up, sideways, down, forwards, backwards. The one on the left is even more incredible because you can see all the little lenses in that orangey area. It wraps around the whole front of its head. So that's another one that could see in every direction, basically. So these are not guys that walk around on the seafloor. They're trilobites that actually could swim somewhere higher in the water column. So beautiful to actually look at features like that and reconstruct what kind of paleo environments the animals lived in. Oops, slow response. All right, who can guess what my punchline is for this slide? There's a lot of trilobites there, aren't there? These all live in my house. I'm not a trilobite collector, but I seem to have accumulated quite a few of them. But the punchline is that they are incredibly diverse. So more than 20,000 species have been described of trilobites. I read one place more than 25,000. I've not counted them, but that's a lot of different species of animals. And that, of course, is a feature of the arthropods. So in the present day, the arthropods, they are the most species-rich phylum. And they were that way right from the very beginning. If you go back 521 million years early in the Cambrian, same thing. That was the most diverse phylum on the planet. And what's really interesting is if you look at the two people that discovered the natural selection mechanism of evolution, so that's Alfred Wallace, Charles Darwin, both of them were utterly fascinated by the diversity of beetles. Both of them had collected beetles. Wallace had collected many, many beetles over in Southeast Asia. So both of them had that prepared mind of the diversity that can result from evolution. So that's the punchline, actually, of that slide. I've more or less organized them from oldest to youngest at the top. So Cambrian, early Cambrian along the bottom, later in the Cambrian, into the Ordovician up here, into the Silurian over here, Devonian at the top, Carboniferous, Permian right at the end, the very last ones, the ones that were wiped out by the biggest extinction of all, nearly 252 million years ago. And Oliver here, your curator in the museum, found a trilobite very much like that about a week ago here in Yorkshire. So that's pretty nice. All right. And then I think this is the last slide just to talk about the diversity of trilobites and how very varied they are. Probably why they're so charming. Yeah. I put spiny to smooth, tiny to huge. So the one on the left, the Cambrian trilobite called Zacanthoides from Utah. And you can see it's got spines all the way down the side of each segment. And it's also got a row of spines along that central pleural lobe, not pleural lobe, the axial lobe. So that would have been a very, very spiky mouthful for anything that wanted to put it in its mouth. Good reason to have spines. This is also a trilobite, but totally contrasting, isn't it? So it's a bit reminiscent of that, the woodlouse that I showed earlier, but even smoother. So those are its eyes over there. That's that pygidium, the tail shield, and it's utterly smooth when it's rolled up for protection. Now, that's from the Ordovician of Russia, by the way. The two on the right are both from Wales, and one is Cambrian, and one is right from the base of the Ordovician. And this thing is the largest British trilobite, called Paradoxides. So that specimen is about like that, something like that. I'd have brought it, but it's much too heavy to carry. That specimen there is at the same scale as that trilobite. And the trilobite, an adult, is just down there, 2 millimeters long. And here it is seen a bit bigger. So that's something called Shumardia. Again, trilobites, huge, minute, tiny, so fabulously diverse. All right. I'm going to show you just a couple of slides on the history of people finding out about trilobites. And then we'll move on to the really special things, which are the trilobites with the limbs and the antennae and the internal organs preserved. So this was the first illustration of a trilobite, published 1698. And it started up as a letter. And it was a letter between Edward Llwyd, who was the keeper of the museum, the Ashmolean Museum in Oxford. And he'd written to another guy, Martin Lister. And these are pictures of them. They look the same because they're both mostly wigs. But the guy on the left is Edward Llwyd, and this is Martin Lister. And Martin Lister's a really good Yorkshire connection. So he set himself up as a doctor in Skipton in 1669. Then he moved to York in 1670, where he was part of a group called the York Virtuosi. And for people that know York, they used to meet in a place on Micklegate. So he actually published the first ever paper with a fossil illustrated in 1673. And the fossil was not a trilobite. It was a crinoid from Clitheroe. So really nice Yorkshire connection. You've got these intellectuals writing to each other. And the text is quite funny because he talks, so Fluid talks about, we've been on our travels, it's been tolerably successful, and they found some figured stones. And then he particularly mentions one, whereof we found great plenty, must doubtless be referred to the skeleton of some flatfish. And that's the picture over there. So this is our earliest illustration of a trilobite. So 1698, published in the Philosophical Transactions of the Royal Society. And here it is. So this is my specimen of this thing, called these days Gigacorella debuchii. But it's quite fun to think, if we turned up and we split that rock and we looked at that specimen and we had no context at all about fossils, what would we call it? What would we think it was? And I was thinking about that on the train on the way down here. I was thinking, flatfish is not a terrible idea, actually. And the illustration was really, really good. Now, this is the trilobite I showed you a moment ago to illustrate big compared to tiny. And this is something called Salter. And he found it by accident. He was in his boat and he came into a bay that he thought was one place, but actually it was somewhere else. So it's a little bay called Porthuroar in southwest Wales. And then he found pieces of this huge trilobite. And this is his reconstruction of the whole thing from 1863. And he's missed bits off, of course. If you look down the pygidium of there, you can see that there are those long spines there. So that was a really interesting find and a really huge thing. So that last fossil, if you read this book, so if you're interested in trilobites, I really recommend this book because he's our high priest of trilobites, Richard Fortey. And his very first trilobite that he found, aged 14, was one of those paradoxides in that same place that Salter found his in 1862. So it's a really lovely book to read. So I was thinking, when did I first find a trilobite? It was also an early teenager, but it wasn't one of these old Cambrian things. It was actually up in the Yorkshire Dales, behind the town of Settle in the Carboniferous limestones up there. Same kind of age as the one that Oliver found a week ago. So Yorkshire's quite a nice place for finding these Carboniferous trilobites. And then another Yorkshire geological hero, John Phillips. So he was the keeper of the collections in the Yorkshire Philosophical Society in York. He has a beautiful book, and you've got a copy of it there in the museum next door, open at a page showing a map of the geology of Yorkshire. This is a page out of that book which shows in 1835 his finds of trilobites from the Carboniferous of Yorkshire. And they're pretty similar to the ones that you've been finding, I guess, Oliver. Yeah. So as usual, you normally find the bits that have been shed as the animal's been growing, and ecdysis it's called, where it loses all the little different component bits of the skeleton. But every now and again, that's actually like the one you found, that one there, the unrolled one, and that's a stretched out one. All right. So that was a little intro to give you a flavour of what trilobites are and some hints at why they're so fascinating, incredibly diverse, long-lived, lots of different paleo environments, and quite nice the historical story of humans starting to find them. All right. So normally, all you find are bits of the exoskeleton because that was stuff that wasn't edible, basically. It's hard, not edible. Every now and again, in the geological record, there will be a deposit which really remarkably preserves the soft parts. It's pretty hard to do because normally, if you imagine a little carcass on the seafloor, everything that's edible will be eaten unless something happens to stop that. And basically what you need to happen is for new minerals to be precipitated quickly before all of the soft parts are gone. So big scavengers can eat bits of the carcass. And even if there aren't big scavengers, there are whole realms of different kinds of microbial communities that will consume all of the soft parts of a carcass. Is something different has to happen, and that very rarely does happen. Now, people found quite early some of these examples. So I have this beautiful volume from 1920s, Percy Raymond, who was professor at Harvard at the time and a specialist in trilobites. And he dedicated the volume here to Charles Beecher. So Beecher was someone that went out exploring in the Ordovician of New York State. And he found one thin layer where trilobites, they looked like they were made of gold. So they were all preserved in pyrite, but they had their antennae and their legs. So something really, really astonishing. And that is a reconstruction of the trilobite that he found, something called Triarthros. And you can see a massive legs, all of them pretty similar. They're different sizes. Antennae up at the top. That was one key early find. And I'll show you some more recent finds from the same general outcrop belt. And this one over here is something called Sororus. And a guy called Charles Walcott, who later found the Burgess Shale, for people that know about that. It's really spectacularly exceptional preservation in the Cambrian of Canada. So this was different. This is in a limestone. Lots of serial sectioning to see the limbs preserved, and a different mechanism. And then here you can see, so it's a picture from above. You can see something about the legs. They're biramus, two branched. So there's a bottom part of these legs, which is for walking on and doing other things with, like burrowing and stuff like that. And then there's an upper part, which has got like a branch, but all these fabulous fine filaments, they're gills. Yeah, so that's a feature of both of those trilobites. Every single segment with a name. I think I can remember them, but we won't. All right, so I'm going to show you some pictures. And we're going to go Cambrian, we're going to go Ordovician, and we're going to go Devonian, because these are time periods where there are some of these exceptionally preserved units. So the Cambrian's pretty interesting because you don't often see the real soft parts, the guts, preserved in fossils. But this is a really famous specimen from the Cambrian of Utah. And you find it on the front covers of books, and you find it in quite a number of papers. But if you look down the middle of that trilobite, you can see there's a structure up at the top. That's called a hypostome. It's a little plate there that protects the stomach of the trilobite. And then you can see that dark feature down the middle. You can see it goes all the way along the axis. But do you see at the top there are these little projections sticking out? Yeah. So those are little digestive pouches. They're called gastric ceca, part of the digestive system of the thing. So incredibly difficult to get that preserved. So what you need is for that structure to be mineralized, turn into another mineral before somebody could eat it, basically. And somebody has been eating it usually, and it'll be one of the microbes. And which of the microbes depends on what was the environment there. Was there oxygen? Was there not oxygen? Because microbial communities, that is a whole domain of knowledge. There are aerobic ones when all the oxygen is used up. There are nitrate reducers, iron reducers, manganese reducers, sulfate reducers, and then there are others that eat the sulfide oxidizers. Lots of different microbes. So what's happened here is that a new mineral has precipitated, and it's likely to have been apatite, calcium phosphate. But these rocks have been a bit metamorphosed. So whenever I've looked, I found chlorites. There are other minerals that it's altered to. So that particular specimen is reused in lots of other papers. And this is one of them, Ortega Hernandez and Brena, 2012. So you can see, so the stomach is up here under that plate, the hypostome. And there is the gut going all the way down to its anus down there. And then these elaborate structures on the sides like that. So that's a pretty exceptional specimen, and it gives you an insight into the digestive system. Just been checking that nobody's gone to the shop to nick things while we were doing the talk. And here are two more examples. So the one on the left is also from the same formation as that last one, the Weeks Formation of Utah. But once again, you can see the stomach area up at the top, and then the gut coming all the way down to there. This is from a different unit, the Spence Eocochaspis, also from Utah. But here you can see the gut down the middle, and you can see all those little side structures, the little pouches, and some antennae up at the top. Now, these are quite interesting. So these are from right at the very beginning of the history of trilobites, from the Lower Cambrian. So the one on the left is from a place called Kangaroo Island in Australia. And that's one of the trilobites that has got a unbelievable number of segments. You can see there are a couple of spines at the back, and then there are loads more segments as it tapers down. But once again, a beautifully preserved gut down the middle. Now, these two here actually are both from the Lower Cambrian of China. You see, this one has got the antennae, and here we can also see all those little paired structures, the gastric theca. And this one has been dissected to show the legs. So in these, you actually get both. You get the guts and the legs. Whereas in quite a lot of the other specimens, we have guts preserved, but we don't have any legs. And that's just, what were the chemical reactions, the biochemical reactions that were going on after the animal had died? Let's look at the Ordovician. So now we're getting into this zone of Charles Beecher, that picture and the dedication of that volume that I showed you earlier. So Ordovician, New York State, this is the kind of thing that Beecher found. So you can see the trilobite, it's got lots of segments. It's a group called the Orlanids. And you can see in the left, you can see there are limbs sticking out. Yeah. And it's got the antennae up at the top. If you look carefully, if you look at those limbs, you'll see they're in pairs. One of them is quite skinny. I'm not sure I can reach over here without pulling the cable out. But there's quite a skinny one, which is the walking leg. And there's one that's a bit fatter, and it's got some little filamentous structures. So those are what's called the exopods, the ones that are held up higher and have got the gills on. Just beautifully laid out, replaced in pyrite. And I made a scan of this a long time ago. But here you can see the legs sticking out that we can see at the surface of the fossil, and you can see there are more inside the little legs down that end, and there are a number of other legs beneath the head shield. And then looking up close, the antennae have got fabulous details, little seta, as they're called, little tiny hairs sticking off the antennae. So really beautiful things. And this is one of my favorites because it's a little bit irregular. So you've got one antenna that's swept forward, one antenna that's swept back, and then the legs. Look at the legs. Can you see the ends of each leg? Got three little claws. It's just amazing detail. Yeah. These are the walking legs, and then on the outside, you can probably see them here. These are the ones above in this view above, but actually in reality, in this view below, in reality above the walking legs. Those are the upper parts of each of those paired limbs. Really spectacular. So what's nice when you get a situation like that, you get a fossil that's preserved in pyrite, which is very dense, and it's in a mud rock, which is not very dense. You can go about making images of these things with X-rays. So you could do it just like in a hospital, expose X-radiograph, get an image, 2D. The last talk here on the vampire shrimp, we talked about this 2D X-ray vision versus 3D X-ray vision. But these days, it's relatively easy to make three-dimensional X-ray images of such features like that. So I'm going to show you some of those. So this is it's the same species, Triarthras etoni. I was going to have this as the cover image, and then I realized that it's a kind of optical illusion that will leave people feeling seasick. Trilobite vertical with, but at least it has that effect on me. But you can see all of the fine detail, the little claws at the end, the antennae at the top. And I showed this last time on the vampire squid, but this is the machine that we use to make these kind of images. So this is Hijaz Kamal in our CT lab over in Kuala Lumpur, and that's the machine that we use, Zeiss X-Radia. And inside here is the little stage which rotates, and here is our X-ray source over there, and you can choose your filter depending on what you're shooting. And then we've got a sensor over on this side, and then basically what you do is you just rotate the specimen in lots of small increments, and then the images are collected on the sensor, and then the software compiles it all together and gets everything placed in the right place, and then you end up with a stack of slices. and it's got a grayscale to it. So the denser the material that the X-rays have gone through, the bigger the attenuation. And the less dense stuff, of course, no attenuation or not limited attenuation. So with images like that, you can now explore in 3 dimensions what's the geometry in that rock, and that can be really good fun. And this is really just on the surface, but you can see all the fantastic detail. And I haven't really done anything with this one yet, but what you can do, and what I've done in lots of other specimens, is go in, take out something that's of interest. You can segment it. You can then scale it up, and you can print it out in 3 dimensions and have a look, in your hand. Really, really useful. So this is another quite famous specimen because of its symmetry. Effectively, it's a large one. It's very symmetrical. So you quite often see this one used in talks. And this is the one that I said was the inspiration for giving this talk. So this is a little specimen that I brought a couple of weeks ago to the machine along the road. It's really quite small. But so that's what I did there, was segment out the pyrite and then scale it up times 7, print it out, and then in an attack of childlike finding some paints, gave it some paint. I need to go back and do it and a bit more carefully, actually. But then, so it looks like a sculpture, doesn't it? But no, that is the actual 3-dimensional geometry in the rock of that fossil. I've just scaled it up and printed out, and now I've got a physical object. Feel quite impressed that you can do that. So Jake Keane had a little play because he was involved in acquiring the data. So he made a little movie out of it. So you can see, it's on the surface of the rock, belly facing outwards. So what he's going to do is he's just faded, changed the contrast. And these are little framboids, because if you look at them close, they look like little strawberries made of pyrite. Not strawberries, raspberries, sorry. And then it's a bit crude. That can be improved, but as soon as you get some inconsistencies in how the spines have been pyrite, then you have to go in and clean it up. But then essentially that could be done very, very quickly. That's the kind of thing you can do. Now, these are from Morocco. So you can see the colors here, yellows and oranges. So that's not pyrite now, but it once was. So the same kind of mechanism as for the previous ones from New York. Very, very early on, we've had a combination of sulfide in the pore waters, hydrogen sulfide, and iron in the pore waters from the sediment. So the microbes working away on the little carcass there have enabled that combination to happen to preserve the specimens in pyrite very, very early on. So what's happened here is deep weathering. So the pyrite is all weathered. And what we're left with are all these iron oxyhydroxides, which have these spectacular, oranges, yellows. And look at the antennae. This one is the Bavarija. I want to pronounce it in Spanish. You probably shouldn't. Bavarilla, I suppose. Have got amazing details on those antennae, again with a little tiny side hair, CT. And this one has got the antennae curved over there. And this big structure here is its stomach. So underneath is the hypostome, the plate that protects the stomach. So it's just showing through the top of the glabella. And you can also see the gut coming down the middle there. You see that? So another fabulous specimen. And just very, very few places where you can see this kind of thing. So now we're going to go to the Devonian. And in the Devonian, there's one other deposit, like the New York Ordovician, where the fossils are preserved in pyrite. And it's near a little town called Bundenbach, being collected for quite a long period of time. So this is the quarry. The little town of Bundenbach is over there at the top of that hill in the distance. And this is a quarry that is excavated for roofing slate. Bochum is the company that does that. And there's a beautiful experiment there where they actually effectively made a square section column. They pulled it out of the rock to actually then document all of the different fossils that were found in different layers all the way through. And this is the kind of thing that you find in there. And these are some of the most beautiful ones of all, I think. So that's a chotocops over there, one of those facopid trilobites. But you see all the walking legs all kind of touching together down the middle. And you just see some glimpses lower left of the upper branch of those two branched legs, the exopods with the little gill filaments. And here's another one, Rhenops. Again, all the legs are like this, all the way down. Here its antennae are curled inwards like that. And not much to see there on the exopods, but they are there. They're all the way through there. And I've made scans of those. I just haven't got around to doing anything with it yet because it's not quite as contrastful as the Ordovician one that I did recently. So what have we seen so far? So you've seen trilobites are very diverse, very fascinating creatures. They're arthropods. Now we've seen their guts. We've seen where their stomachs are under that hypostome in the head. We've seen that they've got lots of legs, pretty much all the same, different lengths, but pretty much all the same from head to tail. What did they do when they were alive? So we don't have any option because they've been extinct for more than a galactic year. We can't observe them. We can look for analogues in the present, but there's one way you can look at their behaviors, and that is looking at trace fossils, so tracks and trails. You can look at walking tracks, burrowing trails, and there are some really beautiful places where you can do that. You can do it in the UK. I could have used an example from North Wales, but I'm not going to. Going to go for something else. So that's one way. That's one way of looking at what they did with those legs when they were alive. So I'll take you to an example. So this is not North Wales. It's Cambrian and it's in Oman, in Arabia. And we're a bunch of sedimentologists, so we're only interested, obliquely in the fossils and the trace fossils. And we're more looking at the architecture of the sandstones and looking at sedimentary structures, which were the paleocurrents flowing. So this is my tent there, and we've just camped here. It's a syncline, where it's like a bowl-like structure. And also the only time I've been in a sandstorm, but I was inside the tent, but still the sand gets inside the tent and in your ears and your nose and in your eyes. But a beautiful, beautiful place. It's a kind of wilderness area. Hukuf is what it's called. And you can see that there are ridges, aren't there? Thin beds that are kind of more resistant. Yeah, so giving you that shape of showing where the strata are. And Forty, once again, Richard Forty, who wrote that book about trilobites and many, many scientific publications, he'd also been to this place. So here's a general view. So you can see all of those layers, very, very laterally extensive. Each one of those is a sandstone. It's a thin sandstone deposited when there's been a storm and sediment has been moved offshore. And then when you turn them over, those sandstones, what do you see? Can you see this structure here? It's quite long, isn't it? That's my camera lens cap. Another one over there with lots of furrows, lots of like ridges pointing in a chevron kind of shape. So let's see. I put a quote from Forty in that book. Yeah, absolutely right. Sandstones and limestones formed low bluffs. So if you follow a single bedding plane, you can crawl on your hands and knees over a Cambrian seafloor, which preserved every scratch and footprint. So the scratches and footprints, those were made in the mudstone. And then the next deposit of a sand-laden current has then preserved the mold of those scratches and marks. So when you turn it over, that's what you're looking at. And he's very poetic in his writing, Richard Forty, and he was really delighted that sometimes when he turned over a slab, there'd be scorpions there. Just from, well, there are lots of scorpions there. Just for the relationship between trilobites and scorpions. Which reminds me of a school activity of my kids, which was to turn over rocks and then collect what you found. And then they took me out to the same area, and you only have to turn about 2 rocks over before you find the first scorpion, ushered into its jam jar. And then Forty, he went further. So maybe we are getting as close to a particular moment of trilobite time as we ever should. one scrape of a limb, one flick of a hair. So this is, I mean, if you've got the right imagination, this is something that's a bit magical about looking at these trace fossils. That was an actual trilobite walking over that structure. Or in fact, in this case, this is called ploughing. So all of its legs are digging back in the middle like this. So it's digging into the mud and seeing what it can disturb so it can be eaten. And little things get chopped up and moved along the center line up to that stomach, protected under the hypostome. But when you're looking at pieces like this, so this is I actually brought one piece back. You can see, indeed, all the individual marks where the legs of those trilobites were scratching into the mud to do various things. And if you're interested in that at all, this is a book that's very well worth reading by Dolph Theilacher, Trace Fossil Analysis. So he's another one of these scientist-artist combinations. The book is full of beautiful, beautiful drawings. So here are some of those trilobite trails here, just showing how they vary through time, because of course each different species will make a different set of marks. Some of them have got genal spines at the edges of their cephalon, so they drag a couple of long marks out. Yeah, all kinds of different sizes, different structures on the gill-bearing limbs. But you can see all of those features that I was showing you in that last slide. They're all nicely illustrated in the book. I bumped into him once completely by accident in the Museo de la Plata in Argentina, and he'd just come back from the field. And on some large tables, he'd just been piecing together some of those long Cruziana ploughing traces that I've just been showing you. So complete coincidence. But indeed, he was out there looking at trilobite trails. And then many people, combining the academic research with a bit of imagination and sculpting skills, have actually gone about reconstructing trilobites. And this one is my absolute favorite. So it's made by someone called Alan Drummond, who is a professor of biochemistry at Chicago and a whole bunch of other things. But he also makes beautiful three-dimensional objects like this. So this is a Sororus, which we saw an illustration of earlier. But he's read all the books, he learned about the nature of the limbs, sculpted it virtually, and then he's printed out a prototype, and then he's cast it in bronze using the lost wax technique. So it's absolutely beautiful. It's a lovely object. So that's my favorite one. And this is something that the Chicago University uses as a kind of promotional illustration. So that one is my little Sororus, the real one, meeting his reconstruction in bronze. And then when you turn it over, you can't really see from there, but you can probably, maybe you can, lots and lots and lots of detail, the walking legs and also the exopods with the gills. That suddenly, this is yesterday, suddenly reminded me of a trip in northwest Borneo in Brunei, when a couple of local Bruneians, lovely characters, Mark and Wan, had taken me on a boat up the Brunei River. And they knew I was interested in horseshoe crabs. And at one point they said, I've got a surprise for you. And then out of a box, brought 2 live mangrove horseshoe crabs out. So here I'm holding one. So that's what made me think of it. So it's a girl. So you can tell that because she hasn't got claspers, which the males do. But you can see it's not very much like it's kind of like a trilobite. It's got lots of legs. It's got a tail spine like many of them have. It's got a cephalon. But there are lots of differences. So the legs are very differentiated. There are pushing legs at the back. There are walking legs. There are a couple of little chelicerae up at the front. There are book gills over here. So none of those things are very much like trilobites, but that's as close as we can get. So it's the closest living relative of a trilobite. And yeah, rather wonderful that you can actually see it. And then on the train over here from York today, I was just browsing and I came across a paper that I had not seen before, which is absolutely delightful. So it was a paper from 2022, and it was by Losso and Hernandez. Can't remember the other name. But about a recent discovery in Cambrian trilobites from the Burgess Shale of claspers. So that's what we don't see here because it's a girl, but in the boy, which I haven't got a picture of. I've got some nice videos of this. There are claspers for mating. And then those have now been found in exceptionally preserved trilobites. So beautiful link. I completely missed that. So yeah, really rather wonderful. So that was the talk. And this was the plan, just to kind of check back over. And hopefully I brought them a bit alive for you, these things which are normally static pieces of object in the rock. So we had a good tour of the diversity of trilobites, big ones, little ones, spiny ones, smooth ones, and a little bit about the history of their early discoveries. We then looked at a whole suite of examples of exceptionally preserved trilobites from the Cambrian, the Ordovician, and the Devonian. And then we talked about what trilobites did when they were alive, so the kind of trails and tracks that they made, people reconstructing beautiful examples like this. And then right at the very end, the horseshoe crab, as close as we can get. Not that close, but as close as we can get. So thank you very much for listening, and I look forward to your questions.